In this video, you and I get to take a look at some features that we can implement in a VMware vSphere networking environment. Let's begin. I happen to be a big fan of networking, and networking is a lot like plumbing. And I'm a big fan of plumbing that works as well. It's about getting stuff from point A to point Z. Now, in a traditional physical environment where we have computers on a network, we'd have, for example, a PC. We'll call this PC number 1. And PC number 1 is normally going to be connected over to some type of a layer 2 switch. So let's say this PC is connected to port, for example, port 15 on this switch. And maybe I'm port 24 on this switch. That connects over to a router. And a router usually has multiple interfaces that go to different network segments. And we could have multiple routers and multiple switches. So maybe this router is router A, and it's connected to router B, and router B is connected to the final destination of where we want to go. Maybe there's a server over here. And by leveraging this infrastructure and using protocols that these switches and routers understand, such as IP version 4 or IP version 6, data can be sent from a PC, be forwarded through the switch to the router can forward it down to the correct next hop router, and the router can continue to forward that packet until it reaches the final destination Z, who then gets that data and says, wow, I got data from PC1. And if this server Z wants to go ahead and reply back, it's very likely to go in the reverse direction. And although that return path doesn't have to go over the same exact routers and switches, it very often does in local area networks. Now, what we get to do in a virtualized environment is take our vSphere environment and plug it in or connect it into the physical environment. So maybe, for example, we have VM number 9. Maybe that's our critical server. Maybe that's server X running as a virtual machine. How do we get the packets and the data from this virtual machine out to the physical world so it can interact with everybody else? And the answer is we're going to use a virtual switch. And this virtual switch lives in the brain of the ESXi host. So this dotted blue is going to represent the ESXi host. And let's say for our example that it's ESX1, a specific ESXi host inside of our environment. So every ESXi host has built in, by default, with no extra charge, a virtual switch. And by default, it's given the identifier of 0. So we have this virtual switch 0. And this virtual switch can have one or more virtual machine port groups. So we have some defaults in place, and we can create more if we want to. So I'm going to put PG right here to represent that these are port groups, just groups of ports. And then when we create this virtual machine, or if we go back to the settings of this virtual machine, we can tell it where its network adapter is connected. So this virtual machine has a virtual network adapter, and we simply indicate that we want this virtual machine's network adapter to be connected to a specific port group. So maybe we have a port group for sales, and we called it sales. So great, it's connected. And if we have other virtual machines inside that same ESXi host, and they're all connected to that same virtual machine port group called sales, they could go ahead and communicate directly with each other. Now you might be saying, well, Keith, that's fine, they can communicate with each other, but what about this VM9 and his friends communicating to the outside world? And I am totally with you. And that's why the next step I want to talk with you about is the physical network interface cards on the ESXi host. So on this ESXi host, let's say it has one, just for example, one physical network interface card on the host itself. In the lingo of vSphere, we would refer to this physical network interface card as a VMNIC, a VMNIC. And that term is referring to the physical network interface card, the real one, that is part of the ESXi host. So as a clarification point, these VMs over here, they have virtual network interface cards, and the ESXi host's physical card is referred to as a VMNIC. And if we had several VMNICs, we might have VMNIC 0 and VMNIC 1 and 2 and 3 to represent multiple physical network cards inside of that ESXi host. So here's what we're going to do. Because this is actually a physical network interface card, we are going to take a physical cable, for example, a Cat5 or a Cat6 cable, that has an RJ45 connector at the end of it, and we're going to plug it in to that physical port on the ESXi host. We're going to take the other end of that cable and we are going to plug it into a switch port on one of our physical switches. So let's say this is port 12 on the layer 2 physical switch. So now the ESXi host has physical connectivity to the real world. And that's a good thing, because if we're part of vCenter, this ESXi host needs to communicate with the vCenter server, and it's going to be using these physical network interface cards connected to the physical world to do that. And the last piece of this puzzle, which is virtual, is to go ahead and associate this VMNIC card, this physical interface, with our virtual switch on the ESXi host. And now, with our network plumbing in place, let's take a look at VM number 9 sending traffic over here to this server, maybe server Z. So the packet would leave the virtual machine, it would go into the virtual switch, in this case virtual switch 0, and that would come in on a port group on the virtual switch, and then it would be forwarded out to the physical world. Now this connection right here between this physical network interface card on the ESXi host and the physical switch, that's referred to as an uplink. And then once the switch receives that network traffic, it's going to forward it based on its forwarding information. In an Ethernet environment, that would be based on the layer 2 destination address. And if it was sent over to the router would then make forwarding decisions, which could then forward it down to the router B, and then router B could forward it out to host Z. And then if there's a reply traffic coming from host Z, it's going to very likely go in that exact reverse direction, over to the layer 2 switch, down the uplink to the ESXi host, and then be forwarded over to the virtual switch 0, and then forwarded back to this VM number 9. So as a frame of reference, let's use the blue dotted line to represent the host ESX1, one of our ESXi hosts in our topology. And an ESXi host by default is going to have a virtual switch number 0. And it would be very easy to create, as we have in this example, multiple ESXi virtual switches. Now the default switches that we get with an ESXi host are called standard switches. These are standard virtual switches. So on this ESXi host, I've got virtual switch 0, and I've also created 2 additional virtual switches, all logically software defined inside of ESX1. And this element right here represents a port group, a group of ports, and I've associated these virtual machines with this specific port group called subnet2 sales. So logically, these virtual machines and their virtual network interface cards are logically connected to this virtual switch called virtual switch 2 via this port group called subnet2 sales. And just like we did in our previous example, let's follow the plumbing. This logical port group on vSwitch 2 is associated with VMNICs 4 and 5. That's these 2 network cards that are on the ESXi host. And then these 2 physical network interface cards could be connected out to physical switches in the physical world. For example, maybe this physical uplink is going to go to switch B, and this physical uplink is going to go to physical switch C. So over here on the right-hand side, we have our physical world. And from these switches, they could lead off to routers and other parts of our physical networks. So if this machine, virtual machine 4, sends data on the network, the traffic is logically going to go from this virtual machine to vSwitch 2 via this port group, and then the traffic is going to be carried up one of the uplinks and out to the physical world, off to its given destination, based on the forwarding and the routing that the physical network is doing. So if server Z in the physical world is where we are going, once the packet reaches server Z, the return path can go from server Z through the uplink, and then once it's received by the ESXi host, it can be forwarded logically back to VM4, who can receive that reply packet from server Z. Now, I've got a question for you. Let's say that we have 100 ESXi hosts that we are managing. It would be a huge pain to have to individually manage the logical switches inside of each and every one of those ESXi hosts. So for the benefit of being able to centrally manage the switches inside of multiple ESXi hosts, VMware has an additional option called a distributed switch, which allows us to centrally manage the properties of a distributed switch, and then vCenter can push that configuration down to the ESXi hosts, which are using that configuration of the distributed switch. Which also implies, by the way, that if we're going to use a distributed switch, we're going to need vCenter to implement that, and we're also going to need an appropriate license that supports and includes the distributed switch, such as the Enterprise Plus licensing. Because the Enterprise Plus includes the license feature of a distributed switch as part of that package. There are some basic components that are available in both the standard and distributed switch, and I'd like to talk with you about those first, and then you and I can take a look at the features above and beyond the standard switch that also come as part of a distributed switch. So for the common elements that we're going to find in standard and distributed switches, both of these implementations allow us to connect V2P. Now, what does that mean, Keith? Well, V2P is virtual to physical. So in our example, we have VM number 4, which is a virtual machine, which is logically connected to a virtual switch, but going through the uplink out to the physical world gets physical connectivity through the plumbing, through that network connection. So regardless of whether we're using a standard or distributed switch, either one is going to provide us that connectivity between the virtual and physical worlds. Another commonality is port groups. A standard switch is going to have something called VM port groups. And that's where we logically connect virtual machines and their virtual network adapters to the virtual switch. If we're implementing a distributed switch, we would still connect virtual machines to port groups, except they refer to them as distributed switch port groups instead of VM port groups. But it's the same concept. It's where the connection happens between the virtual machine and the logical virtual switch. Another feature that is included with both the standard and distributed switch is outbound TS. And TS here stands for traffic shaping. And whenever you think of traffic shaping, I'd like you to think of slowing down traffic. And you might think, well, Keith, that's crazy. Why would you ever want to slow down traffic? And the reason is, or the reason could be, that you have some virtual machine. Let's go ahead and pick on VM1 here for a moment. Maybe VM1 is sending so much traffic out from the VM that it's causing congestion and it's impacting the performance, the network performance of the other VMs in the environment. So what we could do is we could go ahead and implement traffic shaping, which says I only want to allow this much traffic per second as that traffic goes outbound from the virtual machine and into the switch. It would put an upper limit on the maximum amount of traffic that virtual machine could send outbound, leaving that virtual machine going into the switch. And so a distributed switch and a standard switch both support outbound traffic shaping as a feature. Another element that's supported by both a standard and a distributed switch is the concept of a virtual local area network, a VLAN. So for example, if we wanted half of these virtual machines to be in one subnet and another half to be in a different subnet, we could create two different port groups, one that's in VLAN 20, for example, and the other one that's in VLAN 30. And then all the VMs associated with this top port group are going to be in VLAN 20, and all the VMs in this bottom port group would be assigned to VLAN 30. And one of the magical things that's going to happen on this uplink as that traffic goes out to the physical world, it's going to use something called 802.1q tagging, which is simply a way of including that VLAN information, for example, VLAN 20 or VLAN 30, as those frames hit the physical switches, so the switches on the physical world know exactly which VLAN those frames belong to. And that feature of VLANs, again, is supported in both the distributed as well as the standard switch. Next, let's take a look at some features that are exclusive to an ESXi host regarding networking if that ESXi host is participating in using a distributed switch. One of the features is mirroring. For example, with a distributed switch, if we were curious about the traffic that VM4 is sending and receiving, we could set up mirroring to take all the data that is going into or out of VM number 4, and we could copy that over to another virtual machine. So maybe VM3 is running an intrusion prevention system or an intrusion detection system. Or it's running a protocol analyzer like Wireshark or Wild Packets. By setting up mirroring, all the packets in and out from VM4 would be replicated or copied and sent over to VM3 in this example. So we could capture, and then if we wanted to with a protocol analyzer, analyze all of that traffic that was going to or from VM number 4. Another feature of the distributed switch is something called NetFlow. And with NetFlow, it's a detailed record of the types of traffic that are going through the network. For example, if you want to know what percentage of your traffic is HTTP, what percentage of your traffic is DNS, who are your top talkers on the network, what are the top destinations, the NetFlow information that you and I can collect if we're using the distributed switch can help us get visibility and see that information from the NetFlow records that are possible from using NetFlow. Another benefit is quality of service. Now, quality of service inside of a networked environment means we're going to give somebody priority treatment. So if push comes to shove and there's not enough bandwidth to give everybody the access they need to the network, we could take one of our critical machines, for example, VM number 2, and give it priority treatment so that the traffic from VM2 would make it through in a timely manner, while other traffic, maybe from VM number 1 or VM number 4, is held back a little bit simply due to the congestion that's present on the network at that time. So quality of service is all about the prioritization of network traffic. Another feature of the distributed switch is something called inbound traffic shaping. Now you might be thinking, well, Keith, wait a sec. Up here of the features of both, we have outbound traffic shaping. But remember, outbound traffic shaping is about taking traffic that is trying to leave a virtual machine as it goes into the switch, the virtual switch, and slowing it down, impeding the progress of that traffic. And both the standard and distributed switch can do outbound traffic shaping as traffic is going out or leaving the virtual machine. However, the trick is that a distributed switch can also rate limit and traffic shape inbound traffic that's coming into a virtual machine. And that inbound traffic shaping, the slowing down of the traffic as it's going to the virtual machine, is a feature that is only found in the distributed switch, not the standard switch. And LLDP is Link Layer Discovery Protocol. An LLDP is an open standard. It operates at layer 2 from the OSI reference model perspective, and it allows two devices to identify what's at the other end of this connection based on the little signals that are sent at layer 2 from each of the devices. So for example, if VMNIC4 was physically connected to switch B, and let's say switch B is a Hewlett-Packard switch, or a Juniper switch, or a Brocade switch, etc. If that switch is running LLDP, the ESXi host, because it can understand LLDP, if we're using a distributed switch, can learn about that HP device because of the periodic LLDP, Link Layer Discovery Protocol messages that are being sent from switch B. Now, LLDP is an open standard. However, there is a similar function in a Cisco environment. Cisco calls it Cisco Discovery Protocol, CDP, and if enabled on an ESXi host, the function of CDP is supported also by both the standard as well as a distributed switch. But regarding LLDP, the open standard, that functionality only exists in the distributed switch function. So if you want the features of LLDP, it's going to require a vSphere distributed switch to support that feature on an ESXi host. Now, a distributed switch is one of those features that's going to require vCenter as a centralized management platform to implement. So in an environment where we have the appropriate licensing for distributed switches, and we have it all set up correctly with vCenter being our centralized management tool, we could manage standard switches either directly at the ESXi host by connecting to that ESXi host and managing that standard switch. We could also use vCenter as a centralized management tool to manage a standard switch on any specific ESXi host that we want to. However, with the distributed switch, because that's a construct of vCenter, the actual creation and the management of that distributed switch is going to be done through vCenter. In this video, we've taken a look at the default standard switch and the optional distributed switch, as well as features that are common to both and features that only exist in the distributed switch. I have had a great time in this video, and I'm so glad you joined me for it. I hope this has been informative for you, and I'd like to thank you for viewing.